Okay, hi everyone. Thanks for coming. Thanks for inviting me. So tonight I want to give a talk that I've titled Making Video Games That Won't Drain Your Battery in 10 Minutes. I'm sure many of us have kind of had the experience when you're using an app, oftentimes a game, and you're playing it and it starts glowing hot in your hand and it's draining your battery. Just kind of talk a little bit about why that doesn't have to be the case. So a little bit about myself first. So my name's Leigh Carey. I'm a staff software engineer at Playco. So Playco are a globally distributed, remote-first company that specialises in making instant games. So I'm born and raised in Perth. I'm a lifelong gamer. I've kind of been gaming since I was like probably 7. At about 10, I sort of thought, yes, I definitely want to be a game developer. Took a while to get here, I'd say. I've got some prior experience in telecommunications and risk management, but sort of in 2019 I kind of got into the gaming industry before moving to Playco. I've been there for about 3 years now. So let's just start off by talking a little bit about why you might want to build a game. So I think game development is a pretty interesting topic, I find. I mean, games are just generally fun. I think most people would kind of enjoy games. But it's also a fairly fun area to study because a lot of the problems that you kind of find in sort of game developments and the solutions that you sort of end up requiring for them are kind of novel. You don't tend to see them a lot in kind of other application types. So let's just kind of start off first by talking a little bit about object-oriented programming, right, for game development. So at first glance, games are a pretty good use case for, classical kind of object-oriented design. So, many games are kind of about, you've got various different types of entities and they kind of interact with one another, you're passing messages and whatnot, and kind of updating their own internal state, right? So pretty classic use case for like encapsulation, so you're bundling data and methods that operate on the data within a single unit, okay? There's also inheritance, right? Everyone knows about these things. Allows the creation of new classes based on existing ones, promoting code reuse now. As we probably know these days, inheritance can be a double-edged sword. You kind of don't want to overuse it, but used correctly, you can kind of then leverage like polymorphism, right? So you can enable objects to be treated as instances of their parent class. So you can kind of like express different types of objects and different types of kind of entities within the game pretty flexibly, just simply using this. Even up to even a moderate level of complexity, many game engines are written just kind of using this. Object-oriented programming, state machines can do a lot of the work, really. So let's just kind of look at a pseudo-codey, semi-Kotlin-y kind of looking code here for a game entity in object-oriented programming. So this is kind of loosely modeled after the structure that's used in Unity, actually, very loosely. So you've got an object that's taking a set of components that encapsulate various aspects of the game world, game inputs, physics, rendering, and so on. The object's kind of got its own internal state, and it exposes an update method, right, to basically delegate the state updates to those components. So we can then kind of create a hero character, for example, right, by instantiating a game object. And you pass in an input component that kind of deals with inputs from the player, like keyboard, mouse, or taps or whatever it might be. A physics component handling operations for heroes. A render component that kind of knows about like sprites, animations, those sorts of things appropriate to the hero character. But you can quite easily modify this to have like an NPC party member instead of the hero. So you can instantiate that using, instead of the player input component, you could pass in like an AI input component, but you can still have the same kind of physics handling, the same kind of render component if it looks like the hero. You could have, an NPC render component if it's kind of got different different animations and so on. But you can express things quite well, just using this. When you have things structured this way, particularly with the use of like the polymorphic update methods on these components, that comes with a price, actually. So when you're, due to the nature of kind of polymorphism in, I think, all languages I know of, really, it means that invoking that update method is a virtual method call, right, with a virtual table lookup. So that has a performance impact. So I want to talk a little bit then about performance, right, and kind of why that matters. So I think performance and kind of how it kind of impacts the end user is particularly important for native app development, I feel. Because, oftentimes mobile devices have pretty constrained hardware. I mean, they're getting more powerful, sure, right? But, they have constrained hardware. They've got batteries to worry about. So if you're able to build an app within those constraints and your app is kind of, snappy and kind of feels good, you'll get better retention. You'll kind of get better engagement from people. And consequently, if the app is kind of laggy or it's, crashing or worse, then people are going to get frustrated. They're going to churn. So being able to, really use your resources efficiently and not kind of like drain the battery and kind of create all sorts of unpleasant experiences for people, it is quite important, and it can be the kind of differentiating factor when you've got a really crowded app marketplace. So just talking about performance, and a key component here is the memory wall problem. So the memory wall problem kind of refers to basically the growing gap between the speeds of CPUs versus the speeds of memory, right? And pretty much over time, that gap has gotten much, much worse. I mean, yeah, they're both getting faster, but CPUs are just leagues faster than RAM. So it kind of means that for the most part, in your kind of average application, the CPU is spending a lot of time and a lot of cycles just waiting for data to be fetched from the memory and then kind of brought back, and then doing computation and then waiting again. For quite a long time now, CPUs to mitigate that have introduced caches, right? So they're the L caches, if you're sort of familiar. The idea of those is they're very, very small, but they're very fast. So, generally when a CPU is trying to fetch data, it will fetch from the L1 cache, and if it's not there, the L2 cache, so on and so forth. And if it can't find it in any of the caches, then it will fetch from main memory, which, is the RAM, right, in this case. So yeah, as I was saying, like these caches are, generally speaking, that the smaller the cache is, the faster it is. So just as a kind of point of comparison, reading data from the L1 cache is about 60 times faster than reading it from main memory, right? What this sort of means, if you were sort of thinking about, a computer system that's trying to do a calculation and then kind of store the result, if you sort of said, for example, okay, so I'm going to perform a calculation, I'm just going to do it in my head, I'm going to take like a minute to sort of, do a calculation, and then I want to write it down. It's sort of the equivalent of doing a calculation in your head for about a minute, figuring that out, then getting in your car, driving down to Joondalup and getting a pen, and then driving all the way back up here and then writing it down on your piece of paper. So the CPU is just spending that long waiting every time it wants to fetch something from main memory, which, as you can see, is not exactly a efficient use of resources. So how can this impact performance in object-oriented programming? Let's just kind of consider we've got a game object, right, and that's kind of got a reference to a couple of player objects, and it's got a scenery, and then that's got a reference to some rocks or whatever. Obviously, extremely simplified example. But you can kind of see even from this that in your typical object-oriented application, the objects tend to be connected by lots and lots of indirect references, right? And also, not only just the references between the objects themselves, but then also the virtual table lookups every time you invoke a method on an object. Also, the object-oriented objects tend to be allocated as necessary, right? Like, on demand, right? When they're kind of needed. The memory is allocated, and it ends up being spread all over the memory space. So because the memory is just, being used anywhere that it kind of happens to be available, it means that in your typical OO application, as we're kind of just shown before, the CPU is just spending most of its time sitting around waiting. So let's kind of translate this to, an OOP game loop. So again, overly simplified. But so let's kind of consider here we've got a game loop. It's kind of processing a bunch of game entities, right? So, each entity has got several components. Okay, each of the components has probably a pretty small amount of data that's relevant to it. Maybe some vectors or a matrix or something like that. And it's exposing a method to perform update operations. So the game is maintaining like a big array of all of the entities in the world. So every tick of the game loop, we are invoking this update method on the entity, right? And that in turn is then kind of calling update on the input component and the graphics and physics component, render component, and all the other game loop components that are relevant to that entity. And that's happening for every entity in the game. And if you kind of just disregard the previous information about CPU caches and so on, you might think, well, that's perfectly fine. But when you start to think about how that might impact CPU architectures and their interaction with memory, you can see that maybe it's not so great. Really, when you kind of like do a bit of a deep dive into this, you sort of see that like this approach is not just thrashing the CPU cache, it's taking it out of the back and beating it. So we kind of look into a little bit more of what's actually going on here. So every time you kind of go through this game loop, we iterate over this array of entities, right? So this array might store an array of pointers to all these entities, okay? So every time we're getting one of the entities, we have to traverse that pointer, and that's a cache miss. And then we get the data for that entity, and then we have to traverse the pointer to the component that it's referencing, which is another cache miss. So then we get the component, we call the update method on it, which is a virtual table lookup. That might, if you're lucky, that might be in the cache, depending on how many you're using it. If it's polymorphic, then maybe not. It kind of depends on the implementation a little bit, but that's kind of a bit of luck involved there. And then we go back and we do that for every entity, or for every component for every entity, right? So you can see that it's problematic. And the problem really with this as well is that we often have no idea how the objects are actually laid out in memory. We're totally at the mercy of the memory manager. And as entities kind of get allocated and then freed up over time, the memory heap is just going to get more and more disorganized. So you kind of end up in a situation where when you're building up a game and the game's getting more and more complex, the more entities you have, the more wasted cycles you end up having, and then the more devices end up overheating or exploding or crashing or hopefully not dying. So what can we do about it? We'll talk a little bit about the ECS, or Entity Component Systems architecture. Has anyone here heard of ECS architecture? Not the Amazon service, thanks. Yeah, cool. Okay, great. ECS architecture is essentially a blend of kind of just general concepts from computer science, programming languages. Like, so for example, components are kind of analogous to, or used in a similar way to, like mix-ins from typical programming languages, so you can kind of compose together a series of behaviors. So yeah, ECS kind of pulls these established ideas together, and it can kind of create a very performant and easily maintainable way of kind of maintaining the information that's flowing around in these systems where you've got large cross-cutting concerns like physics and so on. So just quickly kind of touching on each of these aspects here. So there's the entity. So entity is pretty self-explanatory, right? That's just a general purpose thing. Okay, so in a game context, it's like every course game object is represented as an entity. So that's like characters, bullets, doors, story trigger, and these sorts of things, projectiles and so on. The components are kind of the key part here. The components will characterize an entity as having or possessing a certain aspect, right? And the component contains the data necessary to model that aspect. So, for example, if you have game objects that need to be able to take damage, you can assign a health component to them. Which can kind of model that, or you could have a position and a velocity component and kind of assign that to an entity so that they can kind of interact with a physics system or some kind of system responsible for updating the position of your elements, of your entity, sorry. And then lastly, there's the systems. So the systems are the processes that basically act on all the entities that have a certain set of components, right? So, as I said before, like you might have a physics system, and the physics system will act on all the entities that have velocity and position components, and it will kind of just iterate over all the results and do some physics calculations, and then update the components for that entity. And so at runtime, you can kind of just modify the behavior of entities by adding or removing components. So like if you had an entity that you wanted to become immune to damage, you might just remove the health component temporarily. The ECS architecture aligns really, really well with other aspects of data-oriented design. Data-oriented design is kind of like its own topic, really, but it's got a couple of aspects that are particularly relevant for the performance problems we were discussing before. The first one is componentization. So the idea of componentization is basically the systems are broken down into modular independent components. So when we kind of do this, we separate the data from the behavior. Modeling it this way. Now that kind of is a bit of a violation of your sort of like encapsulation from OO, but modeling things this way can give big performance improvements, and it can kind of help with maintainability for large systems, which I'll kind of get to later on. The second aspect as well is data locality. So data locality is an approach where the data for all the instances of a component are contiguously stored together in memory. Right, so that kind of enables efficient memory access. for the systems, which, again, they can be like iterating over like thousands and thousands of entities, like dozens of times a second. So we'll talk a little bit more about componentization. So componentization backs off a little bit from the kind of OO tendency, where we sort of model the problem domain in code, and it's modeling the solution really. So we're composing components, like I was saying before, instead of inheriting attributes. So entities can kind of mix and match these components together to build up the desired behavior. So you might have a player entity, for example, that's kind of got like a render mesh, and it's kind of got a position and velocity. It might have a physics component that kind of models like gravity or whatever, a collider component, and a player input component which can kind of model sort of like inputs from the device and so on. But you could then have like an enemy entity which has most of the same components, but instead of the player input component, it's got an AI input component, so it's controlled by a different system. But for all intents and purposes, other than how it's controlled, it operates the same way, and it's controlled by the same logic. So NPC component, for example, that's got a render mesh, it's got a position, but it's not moving anywhere. It doesn't need to collide with anything and do anything. It's just got some dialogue options, right? You can have a bullet, let's say. So the bullet can, be renderable as well. It can kind of move around, but it doesn't have physics. So it's not affected by gravity, let's say, or it doesn't bounce off objects and so on. But when it collides with them, it's also got a damage component, which can then kind of encapsulate the data for a damage-based interaction to affect health and whatnot. And you might have like an invisible wall, where that's just got a position and a collider component, but it's not renderable. It doesn't do anything. It just kind of sits there and interacts with things via the collider component. So onto data locality. So when we're kind of modeling our components this way and splitting up the objects into sets of components like this, it allows us to rearrange the data from an array of structures to a structure of arrays. So instead of just kind of having all of your entities and all their references just kind of spread wherever it happens to end up in kind of memory space, you can basically just kind of get all of the components of a certain type and just group them all together into one array, right? So you get like all the position components and just put them all together, one next to each other in a big positions array. And then velocity, all the velocity components and all the different component types go into their own arrays that just contain just that data. So instead of previously for our kind of game loop, we sort of held a reference to all of the entities, and the entities then had references to all of the components. Instead, the game would just have a reference to all of the components, right? And it would just kind of iterate over them directly. And so in this scenario, your entity then is nothing more than a reference, like an index maybe into each of these component arrays. So if we just kind of re-examine this kind of ECS, or the game object as ECS, we've sort of taken out all of the internal state, we've taken out the update method. All it really is here is just a collection, right? It's just a container for the components that are relevant to it. And actually, like in some more kind of optimized ECS architectures, the entity itself might be nothing more than an ID, right? It could just be an integer. And that integer serves the only purpose of being like an array index lookup, right? So it doesn't actually have to keep these indices itself. It itself is the index, and that index is then used to reference component lookups later. So when we re-examine the game loop using the ECS architecture, what we've got here is we've gotten rid of all of this kind of pointer chasing, right? So we're just kind of getting all of the input components, fetching them, they can all go into a cache, and we can just go over the entire lot in one go. And we do that basically for kind of each set of components, and kind of just work our way through the game like that. So we're able to make much better use of CPU caches using this approach. And interestingly, we haven't lost, with this code here at least, we haven't lost a ton of encapsulation. I mean, the game is directly updating the components instead of going via the entities, but it knew about the components anyway because it injected them into the entity in the first place. You've got the components that are still nicely encapsulating its own kind of data and methods. We just change the way it's used. But you can actually take this a step further, because even here, the components themselves they're exposing their own update method. Right, and the components are kind of doing some of the updates. I mentioned before that in a full ECS architecture, we have systems which are kind of supposed to be more responsible for that sort of logic. If we kind of consider that we've got these component arrays around the place, then instead of them actually handling their own kind of update operations that are relevant to them, we can create systems that contain the relevant update logic. right? So we kind of might have a render system that can iterate over all entities that have render mesh and position components, and can kind of just iterate over them and update all of them together. And likewise, you've got like a physics system that can iterate over all the entities that have position, collider, velocity, and perform some physics calculations and kind of like update them as it's kind of working through them. When we've kind of got things modeled this way, it sort of also allows us to make some further optimized decisions, because now that the components don't have any logic associated with them, they're pure data, they become even more memory efficient, right? They're just kind of, like numbers oftentimes, kind of just in memory space. There's no lookups, there's nothing involved at all in terms of kind of like, resolving pointers and so on. It's just pure data. And it kind of means that you can then make sort of even further optimizations about how you want to store this information. So you might kind of, look at your game world and say, hey, nearly all of the entities here have a position element. So we might use the approach I was kind of describing before, where we just kind of allocate one giant array and we just fill it up with position components, and we just store the position for a certain entity at the index for that entity ID. Right, because it's like a fairly densely populated array, so that might be a pretty good way of representing that. But you could then as well kind of look at velocity component, let's say, and say, well, they don't really. There's not a lot of velocity components, relatively speaking. So we might not want to necessarily just have that approach. We could kind of, just have a different allocation model where we just sort of like, allocate memory based on the amount that we need, and then we kind of, have some mapping between the index, the entity ID to the location in the array. But it sort of lets us make those sorts of decisions, right? And we can kind of then, if you're responsible, get better performance potentially than just letting a general purpose garbage collector or whatnot do the job. But as always with these kinds of things, like with great power becomes great responsibility, and you've got to be continuously profiling and so on to make sure you're actually getting a benefit for the extra complexity that you introduce by sort of having this fine-grained control over memory management. So just to summarize, so object-oriented programming, it's great. A lot of games are built using it, and it's a simple approach, and it can kind of handle the game logic and general interactions for most games, really. But as they grow in complexity, you can end up having performance problems due to that growing speed disparity between CPU and RAM, which kind of ends up with inefficient use of the underlying hardware. ECS can then be used to manage complex game behaviors with entities, components, and systems. That aligns well with data-oriented design. So componentization is where you express the entities as collections of data-oriented components, and data locality will optimize the memory access by grouping related data together. And then finally, the systems allow you to interact with components to express the game behavior. Thank you.
Awesome, thanks Lee, that was great. Any questions from anyone? Jared?
Thanks so much, you're a wizard. Sure. I have a question around optimizing for game devices. So you talk a lot about principles of optimizing for battery life for games themselves, but what's the difference between, say, optimizing for like a Switch, a Steam Deck, an iPhone? Are they architecturally pretty similar, or do you have to spend a bit of time doing that?
Yeah, I'm not entirely sure. I haven't really done a lot of kind of cross-platform native app development. I mean, in some ways it can kind of depend on, certain APIs that are available on a certain device, right? But I guess the general, topic here is kind of just more about general computer architecture, right? About CPU and RAM and memory access, which is common across all things. So the kind of optimization that you're talking about is probably at a slightly higher level. That is kind of about specific APIs that a certain device might have available. Direct 3D and DirectX and whatever these kind of things are, which you kind of also need to have optimizations for. But these sorts of optimizations are more for, kind of like CPU optimization, which are kind of just fairly general purpose.
Can you explain how Unity's default system with the game object and components, how that's an ECS, I guess?
I wish I could. I haven't I don't have a lot of hands-on experience with Unity. Unity is one of the game engines actually that does have a sort of first-class ECS implementation called DOTS, data-oriented something or other, I'm not sure. But many game engines actually don't really have a kind of an out-of-the-box ECS system in place. I mean, you've got a lot of games that would often games would then have to implement their own, implementing this in Unreal, for example, you've got to write your own ECS architecture. So having tooling and libraries that support this, it's not particularly common actually. And which I do kind of find surprising because, this is definitely a very strong way to kind of optimize games. And you find a lot of games that are using this sort of architecture to squeeze more out of their games and kind of, get either better performance, more efficiency, or whatever the case may be. And Unity is an example where there is kind of, that framework there. But so I can't really differentiate between how specifically used, sorry.
Yeah, thanks. I did use, it just doesn't have a system. It's like, it's got components and they're added in a similar way to having position but they're controlled by themselves, methods inside themselves or...
So is that just the Unity game object itself, or is this dots specifically?
No, I'm just talking about the default game object plus list of components. It's like it tries to be an ECS, but it just didn't go the whole way there.
Yeah, there is a bit of, I guess, kind of, there is some overloaded terms, right? Because I think you can kind of have like a component pattern. So like Unity's default pattern with kind of entities and components is kind of, I guess usually I think it's more so a way of like expressing dependency inversion. You kind of like, OO solid principles, right? By like, dependency inversion from componentizing, various aspects of the game world rather than kind of just having objects instantiate their own things. Like, just typical good OO patterns, and the Unity tries to promote them. But the dots system, from what I understand, is where it's supposed to be more first-class ECS.
Can I have one more? So I wanted to know if you've ever optimized a game and re-implemented it to have this, and what were the performance gains you saw?
Unfortunately, no, I haven't. I haven't really been able to. So most of my kind of day-to-day work is actually on web-based gaming, like these days. So I'm doing some kind of research in the moment, actually, to WebAssembly and the WASM runtime in browsers, which can actually leverage this sort of technology. And I have used ECS libraries in JavaScript just as a way of managing information, because when you've sort of got thousands of entities, and then you've got let's say a physics system which basically needs to interact with all things, or some position, for example, where a position might be very common. This approach is quite good for just managing the data itself, just rationalizing it. So I have used ECS systems and kind of ECS architecture, but I haven't yet had the opportunity to go right down to that level and kind of try to do some direct allocation like this, which is something that I'm quite interested in, actually. There's a lot of languages can compile to the WASM runtime, which I think is a really exciting space and not really explored all that much in the current game landscape.
Thank you. I have a question. You said one of the ways to store the data is to put everything in one array and use the indexing. If you are using the same index for all of the entity, does it make a lot of blank in that array and make it slower?
Yeah, it's a good question. So it kind of comes down to, I guess, the component type, right? I think I touched on it, I think, kind of on the last slide, right? Where if you have dense arrays, if you have dense arrays, or you can kind of, otherwise guarantee that the index will be consistent across arrays, then just doing a direct lookup that way can work. But if you've kind of got more sparsely populated arrays, you might be kind of using a hash table of some kind, or some kind of mapping between the entity ID and then the location in the array. And it kind of depends to some degree on the type of component, right? Because, you can sort of make those decisions, which is one advantage of this, where you might say, I've got a component that is only affecting or is only relevant to 10% of the entities in the game. And again, this is heavy optimization territory, right? So you only really want to try and make those calls once you have all the relevant information to make those optimizations. But if you do then understand your game well enough, you can kind of then make those decisions and say, well, for this case, I wouldn't use a sparse array with only 10%. The whole thing allocated in memory, but only 10% actually containing any data. You might use a different model, a different way of representing that. It'll still be a contiguous array, is still kind of the key thing. But in terms of how you map entities into that array, might differ depending on the component type.
Yes, but mapping is still using the pointer to go to different part of the memory.
No, I don't. Sorry, I don't mean mapping by a reference. I mean mapping by kind of a key value pair. Right, so you kind of might have an entity ID, which is an integer, to another, another integer value. Right, so you're not traversing a pointer necessarily. You're getting an index directly, which you can then kind of look up. But
you.
again, I mean, some of these are kind of like, best case scenarios. And when the best case scenario is everything is just in an array and you don't have to kind of look up. In the cases where you might have to do some kind of pointer dereferencing, okay, so be it. You do have to for that case, but you can still get the advantage of like other scenarios where you don't need that kind of the pointer reference. So the idea is just to try and minimize them. We're never going to get rid of all of them, but the more you can leverage data locality, the better performance you'll get.